Alright, this is lesson number 92. We're going to be talking about the Pythagorean identity today. So this name Pythagorean might sound familiar. We know the Pythagorean Theorem. We'll see how that connects a little later on. First, we started by going to student.desmos.com. If you were absent today and you still want to go through this activity, you can. I'll show you the code to go on and do that in one moment. Okay, so on student.desmos.com, this is the class code that you would want to use if you want to try to work on this now. Maybe you were absent and you still want to go through it. The code is M7X8 right here. Okay, so this is what we did for most of the time in class today. We started off here. The first slide is graphing a circle. Okay, and here students were supposed to graph a circle with radius 1 centered at 0, so this might be the equation that you use, or you don't necessarily need those zeros, so you could write something. Let's see if someone did it without the zeros. Oh, this person accidentally had a radius a little too big. They did a radius of 4, so if they change this to 1, that would give them the correct circle here. Okay, so with a radius of 1 centered at the origin, which is just 0, 0. Okay, this is the equation that you want to use there. Okay, and then the second question asked students to state the special name for this circle. Okay, we've been using this with the trigonometry stuff we've been talking about. So that circle that's centered at 0, 0 with a radius of 1, we call that the unit circle. Okay. The next screen here had a little bit of exploration with the unit circle. So again, using that same equation from number 1 for the circle, and then typing in this right here where it says cosine A comma sine A. You're typing that in on this line. Okay, and that'll give you a point. It'll also pop up and ask you if you want to add a slider, so add that. And then you want to make it go from 0 to 2 pi. I don't think it'll let you type in pi, so go ahead and just do 0 to 6.3. Okay, that's an approximation of 2 pi. So that'll let you see, observe some things. Okay, here you can see what this looks like. So here's one student. Okay, they have their x squared plus y squared equals 1. That's the red circle. Then the purple dot is the point cosine A comma sine A. And when I push play, you can see that that purple dot goes around the circle. Okay, so that's basically what students observed. Okay, they noticed that cosine and sine is a point that rotates around the unit circle. The point went all around the unit circle. Things like that. Okay, and the next question, or the next slide, was actually our notes for today. So if you were absent, please make sure that you pause here and write this down. Basically, this is saying that we are able to use basically just what we did. So we use the equation of the unit circle. Okay, so a circle centered at the origin with radius 1. And we use the fact that cosine A comma sine A represents any point on that circle. Okay, well, it represents a point with A that has an angle of A. So we can substitute these in for x and y. Okay, so if I substitute cosine of A in for x in this equation, and then sine of A for y, I end up with this equation right here. Okay, so cosine of A squared plus sine of A squared equals 1. Okay, a little rearranging. Basically, I just swapped these two. So it's now sine squared plus cosine squared. And then you'll notice that the squared is on the inside instead of the outside. That's just kind of a little technicality. So again, sine of A, this whole thing squared, is the same thing as sine squared of A. The reason that we do that is because it could get confusing if we just said sine of A squared like this, because this is really just saying you want to square the angle. So instead of sine of pi, you want to take sine of pi squared, which isn't what you want here. You want to take the sine and then square it. So you want to square that whole thing. So just to kind of clarify that that's what we mean, we use this notation here a lot in math. Okay, so our Pythagorean identity, what we're learning today, is this equation right here, okay? We call it the Pythagorean identity, sine squared a plus cosine squared a equals 1. And that's what we're going to talk about for the rest of this lesson. Okay, so once you have the notes here, go ahead and move on. The next slide asks you to remember the Pythagorean Theorem. We're going to talk about how the Pythagorean Theorem relates to the Pythagorean identity. Okay, so I mentioned this at the beginning of the lesson. These two are related. So if you are at home, you can use this little sketch pad to sketch your answer. The Pythagorean theorem, though, just check yourself here. The Pythagorean theorem should be a squared plus b squared equals c squared. Okay. And then the next slide shows a little animation that will connect this to the Pythagorean theorem. So go ahead and watch this for a moment. If I play this animation here, you can see that the blue is the unit circle, and the green dot is just the dot that we looked at earlier, right? It's cosine of a comma sine a. And it's still just rotating around the circle. The added pieces here are that I marked out the cosine and the sine values. So the red segment represents the cosine, and the purple segment represents sine. So we see here it gets close, the red segment gets close to 1 as I reach 0. Okay, and the purple gets close to 1 as I reach pi halves, or and then it gets close to -1 as I reach 3 pi halves here. Okay, so if I just kind of pause in here, let's look at how this is connected to the Pythagorean theorem. So I know that the Pythagorean theorem is a squared plus b squared equals c squared. Okay, and I know that I use the Pythagorean theorem for right triangles, right? So this right here is a right triangle, which means I could think about this side as A. Maybe I should match my colors. So I'll do this side as A, this side as B, right? Remember when we learned the Pythagorean theorem, A and B have to represent the legs of the triangle, and then C is the hypotenuse. Okay? But in the notes over here, remember I mentioned that the red segment here is really just cosine of whatever this angle theta is. Okay, and then the purple side is really just sine, right? It's the y component, so this is the sine of whatever that angle theta is. Okay, and now I'm trying to think, well, how can I write C as something else? But remember that this is just it's the hypotenuse of our triangle, but it's also the radius of this unit circle. So C is just the radius of the unit circle, which is equal to 1, right? That's exactly why we call it the unit circle, because it has a radius of 1. So if I plug these things into the Pythagorean theorem, so for A I plug in sine of theta, so I have sine of theta, and it's squared, right? Because it's A squared. Okay, and then I have plus B squared, which is cosine squared. and that's going to equal c squared, which is just 1 squared, or 1. Okay, so using this Pythagorean identity, or the Pythagorean theorem, using the Pythagorean theorem, we are able to come up with the Pythagorean identity by looking at a generic triangle in the unit circle. Okay, and this is all about to go away. I'm going to clear it, so pause here and write this down if you're watching for the first time. But pay attention as I let this go around again. You'll see that the radius is constant, and I always have a right triangle where one of the legs represents cosine and the other leg represents sine. Okay, so if I play this again, okay, you'll see no matter what the angle is, the radius is always 1, right? That c, the hypotenuse side, is always going to be 1. One of the legs is always cosine, and the other leg is always sine. Okay, so the Pythagorean identity makes sense for this reason. And the identity may seem sort of pointless, I guess, or like random, right? Where is that from? But what this is telling us is that no matter what angle we're looking at, if I take the sine of that angle and I square it, and then I take the cosine of that angle and I square it, and I add those two things together, I'll always get 1. So even if I ask you, what's the sine of 73 degrees? And then what's the cosine of 73 degrees? If you square both of those values and add them together, you get 1. So it's a nice identity, and how we're going to use it for the rest of the lesson is in solving problems. So if we know sine, but we want to find cosine, we can use this identity, and the vice versa as well. Okay, so let's go ahead and have some examples. Okay, so in this example, it asks us to find cosine of A, given that sine of A equals 1/2, and A is an angle in the second quadrant, which means it would be between pi halves and pi. Tells us to use the Pythagorean identity, and we can do our work in this sketch box. So, first thing we want to do is start with the Pythagorean identity, which is this. And then it tells us that sine of A equals 1/2. So I'm going to go ahead and plug in 1/2 for sine. But remember, in the identity, it's sine squared. So I'm going to do 1/2 squared, and then that's equal to 1. Okay, when I square the fraction, I square the numerator and the denominator. So this is 1 squared, which is just 1, over 2 squared, which is 4. Okay, so I have cosine squared of A plus 1/4 equals 1. I'm trying to solve for cosine of A, so I want to isolate it, which means I'm going to subtract this 1/4 from both sides. Remember, when I do that, 1 is really just 4/4, so I can subtract that way. That gives me cosine squared of A equals 3/4. Okay, then I take the square root of both sides, and I get cosine of A equals the square root of 3 over the square root of 4, and that's plus or minus. So this is just plus or minus the square root of 3 over 2. And going back to this, it says that A is an angle in the second quadrant. So I'm thinking, okay, the second quadrant is here. That means that cosine is going to be negative, right? These are the negative x values here. So my final answer will be cosine of A equals negative root 3 over 2. Okay, in this next example, we are asked to find sine now, and we're given cosine. So starting off with our Pythagorean identity again. This time, though, we're going to be plugging in the number that's given for cosine. So I have sine squared theta plus negative 3/5 squared equals 1. Okay, when I square 3/5, 3 squared is 9, and then 5 squared is 25. Remember the negative part here. If I'm squaring a negative, it turns into a positive, right? Negative 3 squared is just positive 9. So I have 9 over 25, and that's going to be equal to 1. I'm also just realizing over here on the side, I wrote the Pythagorean identity with cosine first. It really doesn't matter either way, but typically we actually see sine plus cosine, so just so you know. Okay, so that's why over here I automatically wrote sine plus cosine. Alright, but anyways, back to solving our problem. So we want to solve for sine theta, so I'm going to isolate it by subtracting this from both sides. When I subtract it, I'm remembering that 1 is just equal to 25/25. So I get sine squared theta equals 25 minus 9 is 16/25. Okay, and then to solve for sine theta, I just need to take the square root of both sides. That gives me sine theta on the left. And I get plus or minus the square root of 16 over the square root of 25, which is just plus or minus 4/5. To decide which one it is, as far as plus or minus goes, I'm looking at the problem. I see it gave me that theta is an angle in the third quadrant. So therefore, down here is the third quadrant. So that means that sine is going to be negative here. So my final answer will be sine theta equals negative 4/5. Okay, and just so you guys can see one more example, this is one we didn't get to in class, but same idea. We are given cosine and we want to find sine. So I'm going to plug in negative root 2 over 2 for cosine. Okay, I'm squaring that. When I square a fraction, I square the top and the bottom. So square root of, or negative square root of 2 squared gives me 2, and 2 squared gives me 4, so this is sine squared theta plus 2/4 equals 1. I can reduce that, so I get sine squared theta plus 1/2 equals 1, and then subtract 1/2 from both sides to solve for sine squared theta. I take the square root of both sides, and when I do that, I take the square root of the top and then the square root of the bottom. Okay, so this is plus or minus square root of 1 over the square root of 2, which just equals plus or minus 1 over rad 2, but remember we like to rationalize our denominator. To do that, I multiply top and bottom by the square root of 2, so I end up with sine theta equals plus or minus square root of 2 over 2. Now I'm looking for which quadrant this is in, and I actually want this to say the second quadrant between pi halves and 3 pi halves, because it wouldn't make sense for cosine to be negative in the fourth quadrant. So that was a typo on my part. So this should say that theta is an angle in the second quadrant. Okay, so that's right here. So again, cosine is negative. Okay, sine is going to be positive here. So our final answer would be sine theta equals square root of 2 over 2. Okay, so that's all I'm going to go over for today. Go ahead and work on some of the example problems from this and the problems in the homework, and I will see you guys tomorrow. Thanks.